Hi everyone, welcome to the Jensen Jensen Podcast, where we're here to discuss all things physical therapy, physical fitness, physiology,
health and growth and shrinking, if we're going to start talking about body fat, but we're not doing that today.
Nope. We are discussing muscle hypertrophy. In the last episode, episode 2, we briefly introduced what muscle hypertrophy is.
Hypertrophy is insertion of more proteins in a muscle.
Talked about Henneman's size principle.
Henneman's size principle, which goes a little bit with that progressive overload, because you have to activate, if you want your tissue to grow, you have to activate the high threshold motor units.
Some of the anatomy, kind of macro and micro anatomy, the relevant principles.
And in this episode, episode 3, we're going to briefly touch on ways that you can enhance this goal of muscle hypertrophy.
Yeah, in the weight room, mostly in the weight room, some of it at home, around with nutrition. But for the most part, strategies that you can incorporate in the weight room. We're not going to get too far into the weeds on this. In future episodes, we'll handle, there's really 4 boxes that you'll need to check to make sure your workouts are working for you, that you're going to be growing. And each one of those boxes will handle kind of superficially. So if you think about, like, let's say you have a kid and you're going to send that kid to music lessons. It's piano, it's guitar, something like that. When the kid goes to the lessons, they just want to learn a cool song. It's not like, I'm eager to learn music theory and teach me like Dorian modes and the interval structure. That they're not interested, right? They just want the cool song, and we're going to do that equivalent today, where we'll teach you some strategies to use in the weight room. The theory, we'll do that later.
So let's go ahead and jump right in. Okay, so in this episode, we're going to discuss 4 major ways that you can elicit muscle hypertrophy. But before we do, we want to briefly explain what mTOR is.
Yeah, so muscle hypertrophy can happen in several different ways. So we drive up to Oregon a lot from California, and the road we take is I-5, right? I mean, that's everyone takes not everyone, but many people, most people would take I-5 anywhere between, Mexico and Canada and back and forth. You could also take
99.
There's other ways to get there, but most traffic travels I-5. With hypertrophy, there are many roads to take. There are a few roads that you can take, but the most trafficked road of hypertrophy is mTOR. Now, this is just an eponym. mTOR is an enzyme within a signaling cascade. It's, this thing triggers this thing, which triggers that thing, which triggers that thing. Eventually, it crosses a finish line and ends in hypertrophy. And hypertrophy is just creation of new proteins. So last week, we talked about what hypertrophy is, and it's just the growth of muscle cells, right? A muscle fiber or a muscle cell, if you're inserting a bunch of protein in there, actin and myosin and a lot of this girder structure protein and alpha actinin and titin, and there's a lot of proteins in here. And the more you insert those, the larger that fiber, that muscle cell becomes. And how do you turn on protein translation or protein synthesis? mTOR is the I-5 that delivers most of that traffic.
Good. So that was a brief explanation of what mTOR complex 1 is.
There's multiple mTOR complexes. There's mTOR complex 2 is about like cell survival and ion transport and stuff. But mTOR complex 1, by complex, what she means is mTOR it's a kinase, which just means an enzyme that puts phosphates on things, a phosphorus with some oxygens on it. It attaches a phosphate to things. mTOR complex 1, that enzyme doesn't travel in a lonely, kind of isolated environment. It is surrounded by family members. There's complexes. There's a bunch of proteins connected.
Okay, so let's go ahead and jump right into the first bucket, which we're going to talk about, and that is hormones.
Okay, so again, there's going to be 4 boxes that you're going to need to check if you want your workouts to actually work for you. If
you want your workouts to work out for you,
to accomplish your goals. And hormones, classically, what we think of as hormones is long-range chemical messengers. So you have glands, which are just little specialized structures that squirt out these chemicals that get into the bloodstream, circulate around for a while, reach their target tissue, bind, to often a cell surface receptor. Now, there's going to be some overlap when we're talking about the immune system and chemicals and what constitutes a hormone and what constitutes like a cytokine and what's it. Well, yeah, we'll talk about that, when the time comes. But with hormones, pretty much all your cells, it doesn't have to come from glands. It can come from fat. It can come from, fat cells and your liver and, your stomach and your muscle. Lots of stuff is going to release hormones. But the major hormones we'll talk about now, testosterone or androgens, I'll just use those words interchangeably, estrogen, right? Now, males and females both have testosterone and estrogen. Males have, 15 to 20 times as much testosterone, and obviously women have more estrogen. And then growth hormone, which women actually have more of. Women have more growth hormone, and IGF-1.
Insulin-like growth factor.
Insulin-like growth factor 1. There's an IGF-2, but you're not like a fetus, right? You're an adult. If you're listening to this, your IGF-1 is the hormone you care about. Now, 2 of those are steroid hormones. Steroid doesn't mean like big anabolic sport thing. I mean,
it could.
It can. It can mean that. Certainly in terms of testosterone,
big
anabolic, like performance-enhancing drug, PEDs. But like cortisol, this is catabolic, and so it's just what a steroid hormone means is it's made out of cholesterol. That's it. That's all it means. And aldosterone and cortisone, testosterone, and estrogen. You get into all these hormones; they're made out of cholesterol. And if a hormone is made out of cholesterol, it doesn't really have cell surface receptors. Now, there's some interaction at the cell surface. There are some additional functions, some secondary functions of these hormones, but for the most part, if a hormone is made out of cholesterol, modified cholesterol, it goes right through the wall of the cell, a phospholipid bilayer. So we're in a room. Let's say this room is the cell. There's a wall right here, right? And that wall has 2 layers, right? There's a room on the other side, and so there's an inner wall and an outer wall. If this is a cell wall, it's going to be, get a phospholipid bilayer. There's stuff in there. And among that stuff is cholesterol. And so if you're a cholesterol-derived hormone, you just go right in and you're going to bind to some receptors on the inside, within cellular receptors. And so androgens and estrogen, that's how these things are going to work.
Okay, now that you briefly explained typical hormones, when we say hormones, we're talking about testosterone and estrogen and IGF-1 and growth hormone in regards to muscle hypertrophy. Now, can you explain how these activate mTOR and turn on that complex for protein synthesis for bigger proteins for muscle hypertrophy? Yeah,
so it's important to distinguish steroid hormones from protein hormones or polypeptide hormones. Growth hormone is a protein. Growth hormone is not a steroid hormone. And so growth hormone can't just walk through walls. It can't get inside the cell. And so what growth hormone and IGF, what these have to do is just knock on the wall and say,
hey, let me in.
Yeah, well, just sort of not even let me in, but just shout their message and the inside of the cell is going to hear it. Now, what that means is a cell signaling cascade gets turned on. So protein hormones, polypeptide hormones, these are going to turn on by binding to a cell surface receptor, turn on a signaling cascade. What is the major signaling cascade that gets turned on? mTOR, right? Now, again, there's a Highway 99, right? There's MAPK, there's other things that can happen. But with steroid hormones, the major function, the primary function is genomic. They get inside of the cell, bind to, let's say we're talking androgens, bind to an androgen receptor, and then they're going to bind to your DNA, to what's called an androgen response element in your DNA. And these genomic effects are kind of slow. So steroid hormones, they're not just blasting their effects in 10 seconds, right? This takes time. Secondary effects of testosterone, of estrogen, are a lot of mTOR signaling. So both testosterone and estrogen are going to, the influx of calcium, intracellular calcium, they're going to help get this going, which is going to contribute to muscle contraction, to actual function. Secondary to that, we can see MAPK signaling. So you get a big androgen dose, and MAPK, you're going to get some signaling there. So some hypertrophic traffic on Highway 99. There's also an enzyme that is probably the most catabolic enzyme in your body. Opposite of anabolism, buildup, is catabolism. We're going to break stuff down. We're going to degrade proteins, break them down. We're going to atrophy. AMPK is an enzyme that is going to inhibit mTOR, meaning anti-anabolic, inhibits through multiple pathways.
So it turns it off.
So it turns it off through tuberin and raptor and some direct interaction. But then AMPK will also turn on catabolism. There's a lysosomal system of protein degradation. There's a ubiquitin proteasome system. We can talk about these things in the future, but this is how you're breaking down proteins. AMPK activates the systems of protein breakdown and blocks the systems of protein accretion, protein synthesis. And testosterone inhibits something called LKB1, liver kinase B1, but it's all over, it's ubiquitous, it's all over, there's a ton of it in your muscle. LKB1 activates AMPK. So there are some dominoes here, but testosterone blocks LKB1. LKB1 would be activating AMPK, which is catabolic. So testosterone is anti-catabolic. Testosterone will also increase IGF-1. And through IGF-1, we are going to promote a ton of PI3K, PKB, mTOR, that mTOR cascade, and a little bit of MAPK on top of that. So testosterone does a lot of anabolic things.
Yeah, sounds like it.
Some of it is genomic. The bulk of it is primary effects are genomic, but its secondary effects, which are very potent, go through signaling cascades. Now, estrogen is not as one-track minded like testosterone is. Testosterone is just anabolic, 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 except with fat. Testosterone is catabolic with fat. Otherwise, muscle, anabolic, anabolic, anabolic. Estrogen is less decisive. Estrogen, a little bit catabolic, it's a little bit anabolic,
It's like, estrogen, you think of females and, ask your wife, ask me, what do you want to eat tonight? And they're a little indecisive. Think of it like that.
Yeah, I'm glad you said that because otherwise that would result in a cancellation if I went there. But estrogen, it's less decisive. Now, I will give you some summarizing statements in just a second that'll make more sense, but let's start with AMPK. So estrogen is going to kind of augment AMPK signaling through LKB1 and direct interaction with AMPK. So estrogen is promoting AMPK. AMPK is catabolic and anti-anabolic. So estrogen also is going to inhibit tuberin. Now tuberin, or tuberous sclerosis complex 2, is a inhibitor, almost direct. There's one domino called Reb in the middle, but tuberin is an inhibitor of mTOR. And estrogen is an inhibitor of that inhibitor. So already
double negative.
We have, so a double negative makes a positive, but already we have one catabolic signal and one anabolic signal. Now, estrogen, like testosterone, helps with calcium, so acute performance, when you're on the field or in the gym or whatever. But one other thing that estrogen does is increased growth hormone. So, again, women have higher levels of growth hormone and estrogen contributes to that. Now, if you want to know what estrogen does overall, find a pathological condition, or it could just be like postmenopausal, where it's not really a pathology, that's just a natural course of aging, but anything where you see estrogen, being reduced. Go to the weight room in that condition and good luck growing. Those workouts just don't work. Now, hormone replacement therapy, let's get your estrogen back to, working order, and suddenly your workouts are working again, and you have anabolism in response to, if you're checking all 4 boxes, in response to your workouts. So the sum total effect of estrogen is anabolic, but it takes a circuitous way to get there. It's a little bit indecisive depending on cell type, depending on, conditions, whereas testosterone is just like, grow now, always.
Yeah. Me grow now.
Me grow now. And then, obviously, growth hormone is going to be released in response to some, peripheral stimuli, long bouts of sleep, particular types of workouts. Growth hormone will be released. Now, what's interesting about growth hormone, it's not the anabolic hormone that people think it is, because a really reliable way to release growth hormone is fast. Don't eat.
Yeah.
Just stop eating for the next, 24 hours, 48 hours, something like that. Earlier, I mentioned that the stomach is going to release, the gastrointestinal tract, largely the stomach, is going to release hormones, as though it's a gland too. Lots of things function like glands. And you're going to release ghrelin from the stomach. Now, this is in response to, if your stomach is empty, you're fasting, and it's just lonely and bereft of food, and it's sad.
Start growling.
It just starts growling, but like weeping ghrelin.
Yeah.
And so ghrelin is this GHRLin, ghrelin, growth hormone releasing ghrelin. This is going to cause the hypothalamus to release growth hormone releasing hormone, and then the anterior pituitary is then going to release growth hormone. If you are fasting, do you experience hypertrophy? Do you experience growth?
That would be
that would be so counterproductive to survival. Oh, there's a famine. I better get huge. Synthesizing proteins
takes
is
a lot
really
of resources.
Oh man, that's like the most expensive thing your cells do.
Yeah.
And so your cells are really conservative. They're only going to grow if all of the conditions are right. All 4 boxes are checked. That's the only situation in which they're going to grow. Otherwise, might as well save the calories. I don't want to deplete this electric bill if I don't have to. It's so expensive. So what happens, you get all this growth hormone and you don't grow at all, is there's what's called the hypothalamic pituitary liver axis. So the hypothalamus releases growth hormone releasing hormone. The anterior pituitary releases growth hormone. Some hours later, your liver, functioning like a gland, releases IGF-1. IGF-1 is what does the growing, the hypertrophic signaling. However, if you're fasting, hypothalamus releases, the growth hormone releasing hormone, anterior pituitary releases growth hormone, and that's where it ends. During fasting, you don't get IGF-1, so you don't grow despite the growth hormone. So really, the 3 major hormones we care about, not really growth hormone. What we care about, IGF-1, sort of the critical regulator, this polypeptide hormone, critical regulator of mTOR. And then testosterone and estrogen, which have secondary cell signaling effects. And then how to do it?
How do you activate or release endogenous testosterone, estrogen, IGF-1?
Okay, so the type of workout, here's how you check that box. The intensity has to be high. Low intensity stuff, not gonna do it. You have to have a high volume, right? It's not about the maximum amount of a weight you lift. It's not strength training workouts where you're doing 5 repetitions, 4 repetitions, stuff like that. It's a higher volume.
So like hypertrophy.
Hypertrophy kinds of volume
12
where
to 15
it
reps.
Maybe 10, 12 reps somewhere, but set after set, lots of these sets at a high intensity with large muscle groups, right? If you're doing concentration curls, or like single calf raises or something like that, that's hit the big, get quads and glutes and hammies and back, big muscle groups and short rest periods.
Good.
And then, but one other thing to note here, if you just think about growth hormone, what's the stimulus to release growth hormone? There's a condition called McArdle disease. And if people with McArdle disease are exercising, they don't get a lactate response. Right? Lactic acid, what everyone blames for my burning, it does not cause that. However, what lactate is going to do is trigger the release of growth hormone, because you get people with McArdle disease who can't increase their lactate during a workout, and they don't get the growth hormone release. You get people to really exercise in such a way that lactate levels rise, growth hormone follows in abundance. And a lot of those same exercise techniques cause the release of androgens in abundance
Okay, so if we want more testosterone and estrogen in a endogenous way, we want to exercise high volume, high intensity, low rest periods.
Yeah, short rest periods, but then also big muscle groups if you can do it. I mean, throw some legs in with your shoulder workout if you have to.
Okay, so now let's talk about the mechanical bucket. How do we use the mechanical part to turn on mTOR, which in turn will turn on the protein synthesis?
Okay, so mechanical, all we're thinking is what kinds of loads are being applied to your muscle. So you go to the weight room and you're lifting things. Your cells, your muscle cells can tell the nature of that lift. How heavy is it? How fast are you moving? Is this concentric, let's say it's bicep curls, concentric, isometric, eccentric or eccentric, a resisted lengthening. What angle are you doing this at? How the time under tension, the rate of application of a load. There are all of these mechanical factors, and your cells can tell. They are informed of what it is you're doing. Now, you have integrins are really the major mechanical sensor in muscle cells. I mean, titin is doing it, cadherins. There are other proteins, other mechanical sensors that are detecting the profile of load and relaying that message into your hypertrophic signals. But integrins, this is really the main one. They are inside of the cell. Again, let's say we're inside of a cell here. And so integrins are in here. They're what's called a transmembrane protein. They trans the membrane. They cross the membrane. And so they're in here and they cross the membrane, reach outside of the cell.
So they're both inside of the cell and reaching out.
And outside. And so if you think about the extracellular matrix, if you're in a house right now, or whatever, wherever, you're in a condo, you're in an apartment, or something, you might have a yard right outside of your living quarters. That's the equivalent of an extracellular matrix. And in our extracellular matrix, there's like collagen and glycoproteins. There's all this stuff out there. Integrins are inside of the cell, cross the membrane, and they're interacting with that stuff outside of the cell. They're interacting with the extracellular matrix. And depending on how the cellular deformation, it gets deformed, how that happens, it relays that message indoors and communicates through something called focal adhesion kinase. It's another enzyme, puts phosphates on things, and we are going to elicit MAPK and mTOR, PI3K, PKB, mTOR, those signals.
And that's through mechanical loading.
Through mechanical loading, the integrins are going to notice this. But there's other ways too. So we'll talk about what kinds of loads, how to apply loads in just a second. But there's also what's called stretch-activated channels, these things that help with the influx of calcium. There's satellite cell activation. You have these little cells that are going to contribute nuclei, right, nucleuses, to the muscle, because muscles, it has multiple myonuclei. And then there's something called phosphatidic acid, which if you can activate diacylglycerol kinase. Again, this word kinase keeps coming up. Kinase, an enzyme that puts phosphates on things. Diacylglycerol kinase is going to phosphorylate, put a phosphate on a diacylglycerol. So like a triglyceride, missing one of those, a triglyceride or triacylglycerol, get rid of one of those fats. Put a phosphate on that thing, and suddenly that phosphatidic acid can bind to mTOR, activating it. So there are a lot of pathways that mechanical loading, independent of all the chemicals, the hormones and whatever, independent of all of that, mechanical loading can stimulate growth. Now the type
of workout,
the type of load, go heavy. That's one of them. You can activate, think Henneman-Sides principle, you can activate type 2 motor units, big, strong, fast muscle fibers through time under tension. Right? You did ball squats, right? And you can,
the wall squats.
Wall squats, right? And you can just hold it and hold it and hold it until you're cursing. And you just, oh man, you may be the most loving person in the world, but there's no love in you in this moment as your legs are shaking. And you can activate the big, strong, fast stuff that way, but not in such a way that, integrins et al. Are going to say, oh, it's time to grow. Let's grow in response to this. Cell signaling doesn't really happen in response to this, even though you do electrically activate the muscle fiber. So one thing is load. The other one that is so important is eccentric or eccentric loading. So
and that's the stretch activated channels too, right?
Well, it will work with stretch activated channels. I mean, it's going to work with the integrins. It's just everything, even mechano growth factor. So we talked about IGF, insulin-like growth factor 1, IGF-1, in the hormone section. You have a local IGF called MGF, mechano growth factor. Now, this isn't an endocrine hormone, it's an autocrine, meaning it's not going to get out into the blood and circulate around, but the muscle cells that are under mechanical stress are going to secrete this hormone, and then it helps themselves, right? They create something that helps themselves. So this is an autocrine version of IGF-1, and this eccentric or eccentric loading is going to stimulate more MGF. It's going to stimulate those stretch activated channels. It's going to work through satellite cell activation, and those integrins love eccentric or eccentric loading. So the way up, concentric, kind of does nothing for growth.
So when he says concentric, that's the shortening of the joint, right? The muscle is shortened as well. So you're closing that joint. Eccentric is just lengthening of the joint, lengthening of the muscle.
Right, lengthening against a resistance. You're succumbing to gravity, but you're kind of trying not to. And so concentric does the least. I mean, that's basically just like you're in the control group, or you're like passive stretching or something. Isometric, you're holding in one place. This is second best, but the best for everything.
Eccentric loading.
Eccentric loading. That is going to stimulate all of those mechanical channels. So if you are emphasizing the concentric, that's okay for bone density, right? That's okay for neuromuscular, right? You're gonna work through sort of the nervous system's control over the musculature. That'll be improved, but it's not going to work for growth.
Yeah,
so to check that box
for muscle hypertrophy.
Yeah, now you can improve strength without doing that, but muscle hypertrophy, you want to grow heavier loads and really emphasize that eccentric. I don't care if you cheat the way up, the concentric doesn't do anything.
Yeah.
Have somebody hand you the weight. If
you can literally do this.
You can do this.
Yeah.
And then let it down.
And then,
Or get a kind of a light weight if you're doing one arm stuff and like push down, curl up, push down. Get a lifting partner who can kind of add a little bit of extra weight. Now, be aware that all the muscle soreness, and this is going to lead us into the immune chemical section, but all the muscle soreness is going to come from that eccentric or eccentric phase. So don't overdo it. I mean,
makes me want to go work out.
Yeah, but start light, gradually incorporate this stuff, because like, it's easy to hold it now. Yeah, and then like if you do it, what's called the Alfredson protocol, it's like a heel drop. It's the eccentrics in the calves. Oh, you're gonna have difficulty walking for 5 days. It's really so sore. Easy to do, but oh man, do you get sore, and that can be problematic if you're overdoing it. So don't rush into this, even if you are not a novice, right? You are an experienced exerciser. This is not something to just start incorporating really aggressively.
And don't do it with every set.
No, not with every set. Again, go at your own pace, but be gradual in increasing the amount of eccentric additional stress that you're adding.
Okay, so that's the mechanical bucket. Now let's get into the next section, which is going to be discussing the immune system / chemical markers that can be activated through workouts.
Okay, so as I said earlier, there's some overlap here. I mean, there's overlap with the immune chemical bucket. With hormones, there's some overlap with mechanical. Let's start with mechanical because we just came from there. So we talked about eccentric loading, letting it down and how that's going to stimulate all these mechanical signals. Same thing with a lot of this immune and chemical, but one of these things with a lot of eccentric loading, in that phospholipid bilayer, there's a bunch of fats, right? A bunch of lipids. There's cholesterol in there, but there's also lipids. Cholesterol is not a fat. It's a steroid alcohol cholesterol. Anyway, there's a fat in there called arachidonic acid. It's a 20 carbon fat. As you do a bunch of this eccentric loading, enzyme called PLA2, phospholipase A2, will liberate that arachidonic acid. A different enzyme called cyclooxygenase, or COX, COX, will convert that arachidonic acid into prostaglandins. So with a lot of eccentric loading, with the right kind of mechanical loads, you're going to stimulate the release of arachidonic acid and the conversion into prostaglandins. What makes you sore, delayed onset muscle soreness, it's a day later, it's 2 days later maybe it lasts for 3 or 4 days, something like this. There's a lot going on there, but what's leading the charge is prostaglandin. So with the appropriate mechanical loading, it's going to really contribute to this delayed onset muscle soreness. Now, if people take NSAIDs, non-steroidal anti-inflammatory drugs, there's such thing as a SAID. Ibuprofen is an NSAID. You know, you take your Advil, Aleve. Tylenol is different. Tylenol isn't an NSAID, but most of these drugs that people would take that would, just get them from the grocery store. These drugs are inhibiting cyclooxygenase. So you still release arachidonic acid, but you don't convert it into prostaglandins. The problem with doing that is prostaglandins do not just make you sore, they also activate a bunch of MAPK, they activate some PI3K, PKB, mTOR. Prostaglandins are anabolic. It is a local chemical, a lipid chemical that is anabolic. It just also makes you sore.
So there's a purpose.
There's a purpose. So if you're taking ibuprofen, you are not repairing your tissues appropriately. Comfort is going to get in the way. Ooh, I don't want to be sore. Okay, well then you're going to impair your growth.
Yeah.
Right? You're unchecking up. You're erasing what you could have checked in that box. Aside from that, whenever you have damage, it could be, you're stabbed by a pencil, you're cut, you're punched, you do a heavy workout, immune cells show up. Immune cells always show up to help clean the environment, to get it ready to repair. And then immune cells are also going to release stuff that helps stimulate the repairing. And so think white blood cells, leukocytes, things like macrophages. I think everyone's heard of those. These are releasing anabolic compounds. Interleukin 2, IL-2, interleukin 15, IL-15. Interleukin meaning between leukocytes, white blood cells. And so IL-2, IL-15, interferon gamma, these are cytokines, little signaling proteins that have anabolic functions. Now, it's not just the immune system that's releasing these. Muscle, if the stress is right, if the damage is right, if you're doing eccentric loading, you're going to release this stuff from the muscle too. IL-15, you're going to release decorin and myonectin and BDNF and MGF and SPARC, SPARC. And these are a bunch of myokines, if it's released from muscle, cytokines, right, the little signaling proteins, muscle kinds. And you will release all of these things, and they will have a lot of autocrine effects. We talked about that with MGF, a lot of autocrine effects. There can also be some paracrine and endocrine effects. Think about something like BDNF, brain-derived neurotrophic factor. The muscle is going to release this, and the brain, your neurons love that stuff. So with damage to a tissue, you're going to get prostaglandins, you're going to get IL-2, IL-15, interferon gamma, decorin, lots of things being released from immune cells and also from muscle cells. And that is going to have hypertrophic signaling. And so how we're going to check that box, how we're going to stimulate this, don't take NSAIDs. For starters. No. Now, that's not going to knock out everything, but it will knock out prostaglandins. And then damage a bunch of tissue. How do you damage tissue?
In a healthy way.
In a healthy way. Yeah, don't
don't go stab yourself with a pencil.
Yeah, I'm going to do bicep curls while I also carve my. But in a healthy way. What's the healthy way to damage tissue?
Eccentric loading.
Yeah, eccentric or eccentric loading. That's the healthiest way to damage tissue. So just like mechanical loading, we're going to incorporate some of this. Now, the load itself isn't as important here, but volume is kind of like hormones. And so again, there's overlap all over the place for how you check that box, and there's some functional overlap in how the cells are behaving.
Good. So it seems like eccentric loading is like a key player here with muscle hypertrophy.
Oh, it is. Yeah. That is player number one. Like if you are a team captain and you're picking, gym strategies as your players, eccentric loading. That's your first pick. I mean, that really would be the team captain, but
for muscle hypertrophy.
For muscle hypertrophy. Okay, so that's that box.
All right, so that's the immune/chemical box. Okay, so this last bucket we're going to talk about for muscle hypertrophy is nutrition.
There's a lot to unpack with nutrition, and certainly we're not going to do all of that unpacking in one episode. We'll return to this topic in the future, but for now, we'll just hastily unpack the major points. One of those points is cholesterol. You know, if I'm on a heart-healthy diet, you know, I'm eating a ton of oatmeal. What makes oatmeal, like why it has a heart, like the American Heart Association, you know, it has this little heart on it, is it will lower cholesterol. And one of those mechanisms is anytime you eat fat, you need an emulsifier. You know, if you think like salad dressings that don't have an emulsifier, the oil and vinegar are separated. You're gonna shake it and whatever, but you're not gonna just like dance every time you eat fat. So you have an emulsifier, bile, right? So bile is gonna go emulsify the fat, and so you can actually, you know, use this. And then you just reabsorb the bile. And then you release it and reabsorb it and release it. So if we're thinking like a recycling system, this is about as good as it gets.
Yeah.
However, if you eat oatmeal, there's a particular fiber. It's a soluble fiber. Think about like if you're eating peas, you know, the gummy inside part, that's a soluble fiber, as opposed to insoluble as the, you know, casing. In oatmeal, there's a soluble fiber called beta-glucans. Beta-glucans binds to bile.
Okay.
If you eat a bunch of fiber, where does fiber go?
In the toilet.
To the toilet. And so if you eat a bunch of fiber, you know, in the form of oatmeal, and that fiber binds to bile, you would be reabsorbing your bile, but instead it goes straight to the toilet and you flush it. And when that happens, you have to make more bile. What do you make it out of? Cholesterol. Cholesterol is a major ingredient in bile. And so your cholesterol levels go down. Guess what else goes down if you do that?
Testosterone?
Testosterone goes down, and estrogen, and the binding proteins like sex hormone binding globulin. All of this stuff goes down too. So yes, your LDLs go down, so do your HDLs, so does your testosterone. And so there are studies on low-fat, high-fiber diets. It's, you know, again, cholesterol isn't fat, but if we can kind of reduce the amount of cholesterol we're eating and introduce some fibers that are going to, you know, help lower cholesterol even further, we see long-term reductions in testosterone. Now, if you are on a, you know, low cholesterol diet for heart health, and my, you know, total cholesterol is, you know, 250, and I keep doing that. This isn't prescriptive.
No.
What we're saying isn't to prescribe anything.
All educational. We're just explaining some stuff.
How things work.
Yeah.
If you're young and your total cholesterol is, you know, 106 or whatever, oh man, eat some whole eggs.
I love some whole eggs.
Yeah, if we had one food to pick, like the desert island energy substrate or whatever, you know, food source.
Whole eggs.
Whole eggs. That's
the
it for us.
bioavailability, I think, is
The
1.0.
protein is
like
great.
how our body digests this and uses the protein makeup.
Yeah, and so that will lead
I
us
think
into
it's the best.
That'll lead us into the next section. But let me just say one more thing that cholesterol does is there's a transmembrane, but a lysosomal sensor of cholesterol called SLC38A9. Really, it's an arginine sensor. That's what I'm going to talk about in just a second. But it also senses cholesterol. And one of the things you have to do to make mTOR work is you have to turn it on. You have to kind of flip the light switch. You have to turn it on. And how do you do that? The immune system, hormones, it's growth factors. IGF is doing it, you know, IL-2, IL-15, interferon gamma, lots of these things are doing it. You're flipping on the switch. However, if mTOR isn't there, it doesn't matter. You can turn the switch on and off and on and off. If it's not there, it doesn't matter. How do you get it there? That cholesterol mechanism, that's one way, but that's not the most potent way. The most potent way is through amino acids, appropriate proteins, you know, those eggs. You know, eating those eggs and other valuable you know, protein sources, high quality protein sources.
What kind of amino acids? I know like there's a lot of supplements, right? Essential amino acids, branched chain amino acids. Which amino acids actually do the heavy lifting for muscle hypertrophy?
Okay, it's a really good question. There are 20 amino acids and not all foods are the same. So whatever your food source is going to have different amounts of all 20 of these amino acids. And again, these aren't equal. Our cellular machinery, you know, developed, sort of evolved without any anticipation of chemistry labs that could separate individual amino acids. These things don't exist in nature. Branched chain amino acids would be leucine, isoleucine, and valine. You don't get like branched chain amino acids in nature. It's like, oh, here's like a pelican leg, and that's just branched chain amino. That's not how it works. And so, our cells couldn't anticipate pharmacology and chemistry labs and supplement companies. And so what our cells are doing are looking for representatives, looking for team captains. Among those amino acids, there are like, okay, if 3 or 4 representatives show up, I assume the whole protein is there, right? I see the pitcher, the catcher, the first baseman, the center fielder. All right, the team's here. Let's start practicing. Is the whole team, is all 20 people there? Everyone on the bench? Everything? No, but the team captains, right, showed up. And so in our cells, the team captains are going to be leucine. Oh, that's number 1. Leucine is number 1. It is sensed through something called cestrin 2. And this is a cytosolic sensor. You're in the wet stuff inside of a cell, and it's sensitive, and there's a quadruple negative to translocate mTOR to the work site.
So it's like Uber?
It's Uber, yeah. And so there's these what are called gator complexes. It doesn't matter. You have to inhibit gator 1, whatever. But there's a quadruple negative to do this. And then the RAG proteins, these little GTPases, these little proteins, are the Ubers, the taxis, the Lyfts, the Ubers. In 10 years, nobody
Waymos.
The Waymos. Maybe in 10 years, people know what that is. But the rest of them, I think, will be vanished by then. And yet, the RAGs, they should just come up with a taxi service called like RAG GTPases.
That would be cool.
Yeah, I would take that one.
Yeah, me too.
Yeah, you'd leave
Like,
leave the Waymo over
get
there.
my muscles bigger too.
Right, and some dumbbells in the passenger seat. So you have to activate these RAG proteins to Waymo, right, to deliver mTOR to the work site, so that when those growth factors flip the switch, mTOR is there to start working. And so leucine, that's number 1. That's truly the team captain. Number 2, so we're talking pitcher and catcher, the 2 most important defensive players, I guess, whatever, is going to be arginine. Now, arginine is sensed intralysosomal arginine through that same thing that was sensing cholesterol, SLC38A9. But there's also castor, CASTOR, cellular arginine sensor for TOR, and that's out like where cestrin 2 is. And both of those, if you have leucine and arginine, inside of the cell, you are activating those RAG proteins. Now, what I would say is third place would be methionine. That's sensed through something called SAMTOR, SAMTOR. And what's interesting about methionine is if you are going to translate a protein, you're going to synthesize, manufacture, create a protein, the first amino acid in every single one, what's a start codon, what starts the process, is methionine. So if you don't have enough methionine, this starts the protein. So leucine, arginine, methionine. After that, I would say glutamine would be. There are multiple other.
They're all good. The amino acids, they all have a purpose. But for muscle hypertrophy, those big 3, the leucine, arginine, and methionine. Glutamine
will work through RAG, GTPases. It's also going to help stimulate MAPK. But then one thing that glutamine does is there's an exchange. Let's get more leucine into the cell. How do you do that? Spit out some glutamine to intake, to inhale some leucine. And so there's a swap. Leucine is the most important. So go on now, get to your glutamine to bring in even more leucine. So glutamine works in a lot of ways. There's TARS2 and folliculin. There are other things that are sensing amino acids, but those are the most important ones. And it's important to get a protein that has those in it.
So like the gross vegan protein powders that like are chalky and that are usually like pea or soy or oat protein.
Yeah, all of those are not that good. Now, if you are a vegan, I'm not saying you can't do it effectively, that you can't have an effective diet with the right amino acids. But I mean, particularly all 3 of those, if you look at their methionine content, really low. And so look at which amino acids exist in which foods. And so, whey and egg, meat, and these have the right profile of amino acids to turn on the mTOR machinery. There's a couple of other things to talk about with nutrition, which is carbohydrate and there's a kind. I mean, if you have a lot of glycogen on board, the stored form of carbohydrate, it can bind to this beta subunit. It's a part of AMPK in an inhibitory way. So a lot of glycogen. All right, yeah, you can help inhibit AMPK. You eat a lot of carbohydrate, you're getting an insulin response. Insulin is anabolic. I mean, it's mostly anabolic with like carbs and fats, but with protein too, it's anabolic. And then the last thing I want to mention is hydration. So if you are dehydrated,
like a little shriveled up
you're all
raisin.
shriveled up. Yeah, if your cells, if there's cellular dehydration, the intracellular hydration is decreased, and they get, they become little raisinettes or whatever. Anabolic signaling is minimized. Catabolic signaling is favored. Catabolic signaling predominates when the cells are all shriveled. When cells become more swollen, it favors anabolism over catabolism. And so hydration, intracellular hydration, really does matter. It's not just whimsical old lore. And the cells that are most sensitive to this are the type 2 cells, the bigger, stronger, faster ones.
Bigger, faster, stronger.
Yeah, there's a channel called aquaporin 4, and that's only in the type 2s. And so we see hydration being a little bit more effective with the type 2, stimulating anabolism in the type 2s even more. And so stay hydrated.
Stay hydrated, y'all.
And eat especially get those proteins in around the workouts. So if you go do a heavy resistance training workout, your cells, your muscle cells, are going to be extra sensitive, extra hungry to absorb those proteins and put them to work for quite a while. But I wouldn't wait, I did my resistance training, I'm going to go wait 6 hours before I eat.
Yeah, no.
Okay, it'll still be like extra sensitive, but eat before, eat during, eat after. Incorporate those proteins throughout.
Have that protein shake right after your workout.
Right. Yeah. And so that's basically it for diet for now. Again, we'll return to this later. We can talk about supplements and meal timing and stuff like that. Details for a later episode.
Okay, so that was the 4 buckets. Now, there are some honorable mentions that we're gonna quickly go over, which is lifestyle modifications.
Yeah, lifestyle modifications, there's a lot of tiny, boxes or buckets here.
Yeah.
A big one is gonna be sleep.
Oh, for sure.
So, we could almost just remove that from the honorable mention and make it like the honorable, we all rise when it enters the room. And so sleep, this is where, especially young males really have this diurnal testosterone, meaning we do stuff during the daylight hours, and at night, testosterone is really going to spike. And growth hormone does the same thing, a long bout of sleep, and you're going to get more growth hormone. Now, one compromised night of sleep. And you do have a compromise of your growth hormone, but just get your sleep the next night and you'll have a rebound effect. Now, if you are chronically sleep deprived, you're not like rebounding just like willy-nilly. So you're going to have reduced growth hormone, reduced testosterone. That sleep is really important. Something else to acknowledge is for people who are just starting to exercise, check all those boxes, but it may still be 5 or 6 weeks.
Yeah, we talked about that in the last episode too.
Okay. So the timing of that is just to be aware. But then once you are, some months into your exercise, you're some months into being consistent, at this point, if you're trying to do aerobic training and anabolic, hypertrophic training, they're going to run contrary to each other. At the onset of exercise, for a while, you can make progress in both directions, but eventually your body's going to settle on a phenotype, meaning a sort of a presentation of the body, a body frame, a body type, sort of morphological, and it's going to defend that. And as you do aerobic training, you activate AMPK. And we can talk about this more in the future, but AMPK is that catabolic anti-anabolic enzyme. It shuts off mTOR and it turns on pathways of catabolism, of atrophy. If aerobic training is turning that on and you're trying to do anabolic, growth, hypertrophic training, you're not doing it all that well. Now,
just working harder.
You're just working out. You're burning a lot more calories. You're going to lose more weight and whatever. And protein translation is really expensive, so you're going to lose fat pretty effectively if you are doing a resistance training too. However, after a resistance training workout, you might be 36 hours later still. That machinery is still cooking up new proteins. And so it's like, well, I separated, I did my resistance training in the morning, I did my aerobic stuff, 8 hours later. Okay, but mTOR was still on and you shut it off.
Yeah.
So contradicting, approaches can be a little bit problematic.
Okay, so sleep is important and muscle hypertrophy takes time. And then the last couple of bits, like alcohol.
Alcohol will inhibit mTOR.
Yeah, so
yeah,
don't drink the booze. And then cigarette smoke, like we already know that's really bad for us. Just don't do it.
Yeah.
So that's the honorable mentions.
Those are the honorable mentions.
Now, we talked about eccentric loading and how that's like a main player in activating mTOR and all of these different types of buckets, right? Now, too much of a good thing can become a bad thing. And that's when we will get into the next episode, which is going to be on overuse and overtraining. So stay tuned for that. So that's it for this episode. Thanks for joining, and we'll see you next time. Bye.
Bye, everyone.